like to spend a little bit of time discussing covalent compounds, which are compounds, as you know, where the atoms share electrons so they can achieve a stable electronic configuration. Covalent compounds form between nonmetals because all nonmetals share the problem that they have a number of valence electrons, usually 4 to 7, and they need the octet or 8 electron configuration that the nearest noble gas has, and so they tend to share electrons to get that noble gas configuration. It turns out that ionic compounds have very high melting and boiling points, and they tend to be brittle. For example, table salt, which is sodium chloride, exists as cubic crystals. On the other hand, covalent compounds are typically gases, liquids, or low-melting solids at room temperature. So, for example, nitrogen and oxygen, the major components of the air, are both covalent compounds and are gases at room temperature. In the case of covalent compounds, you have the positive nuclei, and the electrons that are being shared tend to accumulate, or electron density is greatest, between the two nuclei, and electrons are said to be the glue that holds the molecule together. So you have electron-electron repulsion, nuclear repulsion, but then you have the attraction of the nuclei to each of the electrons involved in the molecule. Now, when molecules, the atoms that are bonded together, don't necessarily share the electrons equally. In fact, the only time that two atoms involved in a bond share the electrons equally is if it's a homonuclear molecule. That is, only one kind of atom. So, for example, for the homonuclear diatomic species F2, because both fluorine atoms are identical, in this diagram where color is used to depict electron density, you can see that the green color indicates that the electron density is the same throughout the molecule, so that no part of the molecule is more positive or more negative than any other part. By contrast, if you have two different atoms involved in a bond, there will always be a tendency of one of the atoms to pull the electron density toward it more than the other atom will. So, for example, when hydrogen attaches to fluorine in the gas hydrogen fluoride, you get a very different electronic map, showing in the red that the lion's share of the electron density exists on the fluorine atom, and the bright blue on the other end indicates that very little of the electron density associated with that shared pair of electrons exists on the hydrogen end. So HF is said to be polar, with one end more negative, namely the fluorine end, and the other end more positive. An unequal electron distribution results in a separation of positive and negative charge, and the bond is said to be polar. We indicate a polar bond and a polar molecule by drawing an arrow with a plus at the other end. The arrow is pointing then in the direction of the dipole. In other words, in the direction where more of the electron density resides. And the other end is pointed in the direction where less electron density resides. In order to quantify this bond polarity, Linus Pauling assigned a value called the electronegativity to each of the elements in the periodic table, and he defined it as the attraction for shared electrons that any atom has when it's involved in a bond. This picture, which is similar to the one found in your book, shows a three-dimensional map of the electronegativity of all the main group elements in the periodic table, as well as the transition metals. We see that the most electronegative element in the periodic table is fluorine, and that makes sense because fluorine is both the smallest. It turns out that atoms get bigger as you go down any column, and it's nearest to the noble gas neon, and so if it gains one electron, it will get the electronic configuration of the nearest noble gas. So it wants to possess the electrons involved in the bond so that it can be more like neon. Fluorine is the most electronegative, followed by oxygen, followed by chlorine. And you can see that in contrast, the metals have very low electronegativities, cesium being the lowest at 0.7. So electronegativity runs from 4.0 for fluorine to 0.5 to 0.7 for the metals. In general, electronegativity increases from left to right and from bottom to top. And as I just explained, fluorine is the most electronegative element. The larger the electronegativity difference, the more polar the bond. So the idea of an ionic bond really represents an extreme case of the continuum that goes from purely covalent bonds that exist between identical atoms and ionic bonds that exist between atoms that have such different electronegativities that in the end the electron exists completely on the more electronegative element and doesn't exist at all on the more electropositive or less electronegative element. So for example, if we return to fluorine, which, as we discussed, has no electronegativity difference between the atoms and is therefore a nonpolar covalent compound, and we go back to hydrogen fluoride, where the electronegativity difference turns out to be 1.9, that's a fairly large electronegativity difference, suggesting the HF bond is very polar. But it is not as big, for example, as a lithium fluoride species, where the difference in electronegativity is 3. And with that large a difference in electronegativity, the bond is considered ionic. So most metal-nonmetal bonds have large electronegativity differences and are ionic.